Okay, hello everyone. Good morning. I think we're on. So in this lecture, we'll start first by reviewing the quiz problems from last time. So the first problem was, among the following choices, select the throughput optimal switch scheduling policy. Let me see. Throughput optimal switch scheduling policy that has the lowest complexity. So could you tell me the complexity of these various schemes? For example,
is O of 1.
Right. Max rate as O
Both n cubed? Not wrong.
n cubed, right? Maximum size matching, which you could implement with parallel iterative matching, are what?
N of n.
On.
Oh, all right.
Pick and compare. Well, that's, I think, again, On. So the lowest complexity one is load balancing. Okay, and how does load balancing work? We have two stages, right? A virtual switch that, first operates by, running a round-robin policy that evenly distributes the incoming load to the lambda 1, 1, for example, lambda 1, 2, etc., to the output ports, which are the virtual output queues, evenly. Okay, and then the second stage implements another round-robin scheduler. So on average, every virtual output queue gets 1 over n share of the rate. Okay, so let's move on to the next part. Consider a 2x2 switch that has Bernoulli arrivals at the rate lambda over 2 into each of its virtual output queues. The switch is able to transfer one packet from each input and one packet to each output port in each time slot as usual. Using parallel iterative matching, what is the maximum arrival rate per time slot during the input port, per input port, for which the queues are guaranteed to be stable? Well, we know that parallel iterative matching is a method for implementing what kind of matching? Maximum size, right? Parallel iterative matching is a practical way of implementing maximum size matching. And we know that maximum size matching achieves up to half of the capacity region. Okay, so now when the capacity region is such that, so lambda is in C if and only if summation lambda ij is less than or equal to 1 for overall j for all I, and summation lambda ji over all I is less than or equal to 1. So basically, since the rate of arrivals is lambda over 2 into each virtual output queue, lambda over 2, the sum of these is lambda, and we know that the sum should be less than or equal to 1/2 of the capacity region, which is 1/2. So the answer is 0.5. Any questions? So let's move on to the last problem. The capacity region C of an n-by-n crossbar switch is the convex hull of all the matchings in the corresponding bipartite graph. Accordingly, state whether the following statement is true or false. There are rate matrices inside C that are only supportable with the maximum weight matching scheduler. Now, this is false. Why do you think this is false? Well, to show that this claim is false is easy as exhibiting another algorithm that achieves the capacity region. And we know, for example, with any of the optimal throughput scheduling algorithms, for example, load balancing, we can achieve capacity. Maximum weight matching is one way of achieving capacity, but it is by no means the only possible policy for achieving capacity. Okay, so that was the quiz, and next we'll talk about the new lecture. So I'll stop the recording.